My name is Hernan Diaz Alonso. I'm the graduate programs chair here on SCI-Arc. And I've been given the task to introduce our next three speakers, which the three of them are amazing in their own terms, and also I think it represents a very interesting cross-section about where the crossroad of these issues have to do with architecture as a discipline at large, and how we can start to keep developing this kind of intersection models between multiple disciplines and multiple approaches to the problem. So I'm going to give you just a brief bio of each of the presenters. All of them are incredible accomplishments, so I'm going to do like a shorter version so we can get as soon as we can to their presentations. Our first presenter in this panel, the title of this panel is Synthesizing Behavior, which my English doesn't do enough justice to such an interesting title, which is basically, it's kind of a free-for-all for these three guys to be able to talk about what they do, which is in that realm of things. So our first speaker is going to be Achim Menges, which is, he's an architect and director of the Institute for Computational Design at the Stuttgart University. He's also a visiting professor at the School of Architecture in Harvard, and also a visiting professor at for the Merchant Technologies and Design graduate program at the Architectural Association in London, where he was a professor at the Studio Master of the Merchant Technology and Design graduate program from 2002 to 2009, and Unit Master for Diploma Unit from 2003 to 2006. From 2005 to 2008, he was professor for form generation and materialization at the HVJ Offenbach University for Art and Design in Germany. In addition, he has held multiple visiting professorships in Europe and United States. Achim research focuses on the development of too many complicated words and technicals. Focuses on the development of integral design processes and the intersection of evolutionary computation, algorithmic design, biomimicry, engineer, and computer-aided manufacturing that enable a highly articulate, performative built environment. His research project has been published and exhibited worldwide and received numerous international awards. Our second speaker is closer to home, is Andreas Froech, who's based here in Los Angeles. And Andrea, there is a kind of a weird, we have a lot of sailors in this conference, and we have a lot of people from Austria. So it seems like there is a desire in Austria to keep innovating and figuring out new ways to screw the design world. He received a diploma engineer in architecture at the Technical University in Vienna, and a master's in architecture from Columbia University in 1996. He taught architecture at UCLA, School of Architecture, while working for Greg Lynn firm in New Jersey and Venice. Since 2001, he's the director of material development at Panelists, specializing in production and fabrication processes of lightweight, light-transmitting Honeycomb panels. He holds several US patents for the Panelists cast polymer series panel, and in 2008, he founded Machinist, a custom fabrication service and research company using large in-robot CNC machining equipment with its focus in the architecture and furniture design market. Machinist is located in Los Angeles, is providing multi-axis CNC service for the custom architectural design market. Its focus is large in scale project producing in-house 5- and 6-axis machine equipment. Andreas also assisted the maneuver layer in setting up the Los Angeles office of Panelists. And our last speaker is Bill Chrysler, who is the founder and president of Chrysler & Associates. Before founding this company, Mr. Chrysler was executive VP and production manager for the Performance Salescraft Corporation in Northern California, which is the largest manufacturer of sailboats. Was the largest manufacturer of sailboats at the time. During his 10 years at PSC, he managed the production and distribution of over 12,000 sailboats in 3 models, one of other sailors. So either you have to be Austrian or sailor to be in this conference. Mr. Chrysler has degrees in English and history from San Diego State University, Business-related outside activities and positions include current chairs of Napa Valley Woodforks Investment Board, immediate past president, current executive committee member of American Composite Manufacturers Association, the world's largest trade association for composite industry. He was in the past director of the SPI, Society of the Plastic Industry. Are all these secret societies? Yeah. Okay. And composite, only one member. Okay, that's a good way. Composite Institute chair of the CFA, and the multiple cycles go and on and on and on. So the last thing I want to say in relation to this is a very, Bill, on a personal note, I want to thank Bill because I owe my life to him, in the sense, literally. And I think this defined, I think, his approach and the approach of the three speakers, and I think it's at the center of the problem that we're trying to figure it out, which is a combination of pragmatism and lyrism, or how we can get to friction the desire that we have to do the impossible. So sailing from Mexico with Greg and Bill, Greg Lynn wanted to keep waiting for the wind. We were like 4 hours in the same place until Greg decided to go to sleep. Bill took control of the boat, and he turned on the engine right away because we needed to move. So I think that defined exactly what is the problem, the crossroad between us, architects and designers, looking for the impossible, and the guy who said, we're going to get there, but we have to keep moving. On that note, Achim will be first.
Yep. Thanks for the introduction. I'm not a sailor and only almost Austrian, I have to say, being German. Anyways, today I'm going to talk mainly on the particular research that I've been conducting at various institutions over the last couple of years with the focus on sort of investigating processes of design computing that are actually synthesized with physical materialization in order to actually understand and research how we can actually use what Sanford quite nicely called in this quote the embedded form, which is actually the latent material gestalt in any kind of material system that we deal with, as a starting point for the design process. Of course, at Stuttgart University, that kind of design approach, starting with the physical rather than with the kind of digital or the kind of imagined, has a kind of prominent history. The most probably well-known person actually researching at Stuttgart University was Frei Otto, investigating actually how you can use physical behavior and the kind of self-forming capacities of material systems as the kind of base for a design process. Most famously probably are his soap bubble experiments, where he actually uses the inherent kind of tension within the soap farms to find physical shapes that at the end sort of were at the base of also his kind of probably most famous building, the Olympic Stadium in Munich, constructed and designed in the early 70s. So what we are interested in doing is seeing how we can actually extend such a design process, which actually conceives of form as something that comes from within the materials, something that we actually tease out of those materials as we allow them to have a say in the structures we create. It is nicely put in that quote, by contemporary means. That means that what we try to do is we try to embed in the kind of generative design codes that we use actually the physical material behavior from the very start, and also link into that the possibilities and constraints of contemporary manufacturing processes. So the idea is that you create something that one could call a kind of morphogenetic design approach, in which the kind of genotypic information is actually driven by, or is actually determined by, the kind of materialization constraints of the systems, and then in exchange with actually external influences, such as, for example, the structural forces acting upon the system or the environment interacting with the system, you can unfold a very particular sort of material gestalt. Now, we've investigated this kind of design approach in relation to fiber composites quite a bit, and we did that actually in this particular case with the manufacturer of these kind of knitting machines. There are only two manufacturers that can build these knitting machines, as I am informed. One of them is actually quite close in Germany, and they produce these materials, which is a kind of, it's a nice name, it's a kind of warp knitted spacer textile. So it's a kind of three-dimensionally woven textile. And we investigated the capacity of that textile while being absolutely non-elastic to actually be capable of draping over very complex three-dimensional curvature, double curvature, without the need for any kind of cut patterns, and still with full structural capacity. So what we did is we investigated that behavior, which is mainly driven by the spacer stuff yarns, came up with a kind of mathematical description of that behavior, which then is part of the kind of generative design code, from which we can actually extract a manifold number of possible material gestalts, also programmed an embedded sort of simulation tool to see whether the local and the global stretch actually is feasible. And with that, we were able to construct a number of actually quite complex monoshell kind of constructions like this furniture without actually the need for larger formworks. It's just all driven by the material behavior itself. A number of kind of more complex arrangements, a number of shells bonded together. Here you can nicely see how the kind of microstructure actually determines the shape of the macrostructure. And then we went on to also embed, sort of construct, intervene within the construction of the material itself by embedding additional threads that, by actually simply pulling them, allow the material to self-organize in fairly complex fashion. And if you that sort of calibrate with the forces traveling within the material, you can actually create highly complex, very articulated composite structures, which are as simple to construct as just pulling a couple of strings. The rest is just happening by the material itself, and still forms, mainly due to this kind of secondary undulation, incredibly stable and stiff shell structures. And the same principles also works if you have a kind of closed, completely watertight composite skin on the one side. So here you can see the kind of what makes composites interesting for us is you have a hierarchical build-up. You actually blur the boundary between constructing actually a structure and constructing the material. And you can actually design the behavior into the system. So in order to be a little bit provocative, I thought I'm going to talk about a different composite today, which is probably the oldest composite we know, and that is wood. Nicely stated by Frank Costin, wood is God's own composite. You wonder, who the hell is Frank Costin? That's the guy that actually designed plywood airplanes in the Second World War, then went on to actually design race cars with plywood chassis that were actually pretty successful in Formula 2 racing. So he knows a little bit about wood. What is interesting about wood is that it's actually pretty much a kind of high-performance natural composite system where the cellulose microfibrils are the reinforcement and the lignin is the matrix. Unfortunately, we've lost most of the understanding of how we actually deal with this high-performance composite due to the industrialization, which dumped wood down to being actually a dimensional building element. I think in this country it's emblematic that you don't even call it wood, you just call it 2x4, which is not relating to its anatomy, it's actually relating just to its external dimensions. Who the hell cares what the kind of microstructure is? We do, in a certain sense, and I'll come to that. So what is also interesting about wood is that it is literally kind of embodied solar energy. I'm definitely not part of the kind of ecological Taliban that tries to hijack architecture with ever-increasing sort of quantitative certification of what we're actually doing, but I still find it very fascinating that when compared to the materials we talked about before, namely carbon fiber composites, wood is actually, when you look at the energy that is needed to ensure a given strength in the structural whole, 850 times more energy efficient than carbon fiber composites. Now, if you look at the energy needed to produce a panel of a given compressive strength, that again increases tenfold, so 8,500 times more energy efficient. So what I'm going to show is how we can actually exploit these the possibility of actually thinking about wood as a high performance, fully renewable, actually naturally grown composite material in a different way when we begin to actually take material behavior as the starting point for the design process. So in architecture, there are only very few cases where this kind of elastic bending behavior has been utilized, despite the fact that you can actually get quite considerable structural benefits from it. One is the vernacular sort of reed structures by the Madan people in the south of Iran that were actually able to modulate the behavior of these bundles by the number of reeds and the way they actually sort of taper towards the top, and built a whole number of building typologies from that. And then the other is a Frei Otto kind of construction technique called the wooden lattice shells, which are built as completely regular planar wooden lattices, and then if you just check them up on a couple of points, you can see that here or there, the whole thing actually settles into this particular extremely actually versatile double curved shape completely by itself. It's just sort of the elastic behavior of the wood. Just need to tighten down the joint points, and you actually need to secure the perimeter sort of bearings, and the whole thing is incredibly stable. It's just a 2-inch by 2-inch diameter of the wood pieces. So we started our investigation by actually doing physical tests of the material to be used, elastically bending it and corroborating that actually with the, and calibrating that with the simulation tools where we were to use. That brought us to a kind of form finding simulation, which you can see here, which explains the principle of the system. You have actually two plywood strips. It's birch plywood. These plywood strips are actually bent, and they're not globally bent as in the Frei Otto case, but they are locally bent so that the strips are actually alternating. Here, can you nicely see that again? Strips are alternating between elastically bent and tensioned region. So you may know that, that wood is actually particularly good in tension when compared to the kind of weight to structural capacity ratio. It's better than steel. So here you can see that again. You could say it's a kind of multiple artery bows connected, which have a particular weak point here, and we found a specific way of dealing with that, which I'm going to explain later. So the second aspect, as I mentioned, having sort of understood the material behavior, is how do you actually introduce the fabrication constraints. So the aim here, because that needed to be produced on an extremely low budget, we had to produce everything with one tool on one machine, and that's this kind of 6-axis robot we have in our laboratory, where we basically investigated the degrees of freedom that this machine has and developed all the details to be machined in one go on that thing, because there are 500 pieces, so time was also a bit of a consideration. So you see these strips to be elastically bent. They're connected in the tensile region by a kind of strip that we developed, a joint that we developed. Another detail is obviously the way the thing meets the ground, being so thin that moisture actually becomes a problem. And then the third critical detail being the connection between the strips. And this is actually where the weak point of the system is, because here you can nicely see this is where the two strips cross, and you have zero structural depth at that point. Another kind of parameter that drives the articulation of the strips is the kind of the translucency or the transparency of the system, being actually a kind of almost closed screen that allows for indirect illumination, as well as kind of artificial lighting that actually exposes the light to the outside. So I come back to this weak point, and actually we thought about a way of how we can actually use irregularity in the system to make initially weak elements actually pretty strong as a kind of overall system. And the way to do that was actually pretty simple. A simple strategy is just offset these connection points and also sort of make them undulate around the structure. And by that, while the local weak point is still there, it kind of gets distributed in the system, and the overall system is actually very strong. So that was embedded in a kind of computational code, which also sort of then distributes these connection points in a very irregular, structurally optimized fashion. And here you can see the verification. This is the material simulation of the overall system. Starts with the planar strips, bends them up, and then it actually does exactly what's going to happen on the building side, just connects the individual pieces, and by that, the whole system finds sort of an equilibrium state by itself. So manufacturing data is an integral part of the process, so we could actually mill these 80 strips very quickly. You can see the robot here, and then that's pretty much the building side. You take a couple of students, kind of very lightweight strip, and then literally the material finds the form on site by being connected in a fashion that is kind of determined by the joint points. So in the end, you get this kind of semi-interior extension of the public square at the city center of the, or city center campus of the university, in which actually the envelope and the load-bearing skin is all constructed from this extremely thin plywood material. So actually, the whole, all the elements have a thickness of 6.5 millimeters. That's a quarter of an inch. And that's the whole structure and the envelope. I think what was very interesting for us is that when we discussed the project initially with Frei Otto, is that obviously one of the problems of this kind of composite is that it creeps, so it loses tension over time. So we were very keen on understanding how that is kind of affecting the kind of lifetime performance of this. So what we did is actually we scanned the pavilion a couple of times, first when it was actually immediately erected, and then also after a couple of months. And we were very pleased to see that, first of all, when it was actually built, the form found on site was incredibly close to the form that was actually found with our computational design process. And even over a couple of months with a lot of humidity cycle changes, it remained to keep that kind of inherent tension. We're also working on a number of ways of intervening with wood on the microscopic level. So we developed, for example, at the GSD, a way of scanning the wood pieces we use and then erasing with the kind of laser cutter only the early wood parts because they don't contribute much to the load-bearing capacity. Or we recently also investigated how we can actually merge almost or blur the boundary between the organic and the synthetic composite by using actually chemical procedures to replace part of the wood with actually plastics. So here you can see the same process. The early wood is replaced with another kind of artificial substance. The second project I will quickly show takes advantage of the second interesting material characteristic that wood has, and that is its hygroscopicity. So that means it's actually responding to changes in relative humidity in a kind of real-time fashion. So in many ways, it actually is a smart material. That is, again, due to the fact of its kind of fibrous makeup, where on a kind of molecular level, the water molecules are getting actually attached to the cellulose fibers, and by that, wood actually swells. So we thought that how can we actually utilize that behavior, which we usually try to get rid of? You know, sort of within a low energy process anyways, we spend 70% of the energy in the wood processing just to make sure that wood does not respond to changes in relative humidity. So we thought if we leave that kiln drying out, what can we do with this kind of behavior? And obviously we can actually utilize the hygroscopic dimensional change in order to trigger a shape change, and that could, for example, allow us to construct an environmentally responsive surface structure that adapts to increases in relative humidity by ventilating, automated ventilation. A system that we know that does exactly that is the spruce cone. Spruce cone is growing in a wet, moist state, a high moisture content within the kind of fibrous, actually at fiber saturation point, and then it dries, and once the environment has reached suitably dry conditions, it actually opens, seeds are released, and that's all just sort of embedded as a kind of material behavior within the fiber structure. Funny thing is that obviously the spruce cone just needs to do this once, but it works perfectly over 500 cycles. Tested that actually a lot. So here you can see that again, moisture content decreases, and by that the scales open. So we developed actually a kind of composite of natural wood veneer and a special sort of composite layer that allows to mimic this behavior using very cheap wood as a starting point. And here you can see that this is the simple material element. Here you have the changes in relative humidity, and you see a kind of autonomous shape change just by itself. You can program that shape change, so you can make it actually move this way when humidity increases or make it move the other way. It all is kind of all dependent on the parameters of manufacturing the piece in particular conditions. So we then went on to design a substructure for that, which is a simple folded one-cut thing. We looked at the kind of interdependencies of the kind of thermodynamic influences on the distribution of moisture in relation to the morphology of the system, developed a kind of set of components from that, used a mathematical equation to drive the subsequent surface evolution, which happens in constant feedback with thermodynamic and structural analysis, which led us to this kind of prototype, which we could relatively, despite the kind of high level of articulation, we could build immediately as a functional artifact, which actually changes its porosity with changes in relative humidity. So here you have a system that is actually fully environmentally responsive with no need for any additional electronic or mechanical control. We were not entirely satisfied about that because, in a sense, the kind of division between structure or responsive structure and the actually load-bearing structure and this kind of overriding sort of underlying UV parameterization of the surface didn't make us very happy, so we went on to redesign the system as based on a component in which actually the structure and the responsive part is one piece. It's just that the responsive bit is very thin and the structural part is actually much thicker. And that is actually now in an kind of embedded in an adaptive shape algorithm, which allows the use of multiple components. You can see that, again, a kind of evolutionary process to achieve this, which is the fully functional prototype, accelerated just by sort of a little bit, so it opens entirely in 20 seconds, given an increase in relative humidity from 50 to 80%, and it takes about 30 minutes to close again. So what you see here is an incredibly simple, incredibly cheap, environmentally responsive system in which actually the sensor, the actuator, the regulating element, all is just one very simple wood veneer piece. Currently, we're trying to convince the city of Frankfurt that they need something like this. I think in California, you don't need it. To build a pavilion that is kind of closed in high humidity level, rainy weather. And once the sun comes out, humidity level goes down, it just opens completely by itself. And that sort of allows also a kind of qualitative experience of this environmental changes that always surround us and sort of are in direct exchange with the material behavior itself. Thank you.
First of all, thank you, Marcelo. Thank you, SCI-Arc, for having me on this conference. Machinist is a fabrication production environment that is simply focusing on the utilization of digital power, digital motor-driven tools. In this case, only robots, automotive robots. The reason why automotive robots, there are a few, they're a beautifully well-functioning designed digital tools. They are available right away, so we didn't have to design any machines to get started. They incorporate already a lot of concepts of efficiency, shop efficiency, production efficiency, strength, and accuracy. The automotive industry just has done this already for us. We only need to find a way to take the architecture, furniture, and produce it with robots. Having done 10 years of fabrication, with non-digital tools, like human labor, it's very clear that it's all about using robots is really about not using labor. That's what cars do. That's what our challenge is in this company is to move as much as of the effort to produce a component, a piece of furniture, to move it to the machine, that the machine can do as much as possible, so all your effort as a human is eventually left in there, mostly in the assembly, in some finishing, which is a very highly complex operation that takes a lot of try and error programming, figuring out how to actually program a robot to do sanding, something that's very complicated, or painting, to achieve the finish that you see with your eye. And lost my point, but anyway. So what you're going to see is a bunch of projects. There are about 7 projects, various scale, from small scale to building scale, that all trying to use, that are designs more or less looking for a digital process, but it's not clear where it is. We all need to just find how to use the robot to produce this piece of design. I'll start with a project that's kind of between furniture and building, obviously. It's also the first one. I actually kind of kick-started the whole operation 3 years ago, 2008. The blah ball, Greg Lynn's blah ball. Greg Lynn just, he's handing me what you will see in all these projects is there's a computer model that incorporates all what's required to make the project. And the idea is to accept material as it is and find a way to treat the material, to cut the material, to mill the material, that you end up with the product. So the material is kind of a non-issue, or it is accepted. It's the desire of the architect, it's the desire of the designer to do this in a certain material. I mean, we have a lot of material knowledge gathered throughout those years, so there's a feedback situation, of course, but we try not to change design. We're not trying to change design because of material or because of the process, of the digital process. I'm kind of have the feeling there's always a way to program, to use a robot that you can almost do anything. It's just a matter of what you hang on this robot. So having a model, it incorporates everything we need to do, which is about these cut lines to join these plastic bricks. So we're using all different softwares to establish our data, to manage our data that's then being fed to a robot controller, and the robot controller converts this all into a 6-axis motion that does the job. This is all done. It's really hard to intuitively think about a robot's motion, but that's what you need to use. There's some testing involved so that you have successful motion, and then there's some simulation. Like this is actually a software that simulates a robot within a digital environment. So you have the same robot in there, and you generate the path within the software, which in this case is always normal to the surface of this plastic brick, and manage the order of cuts. These are extremely complicated cuts. It's not even, here's how it actually happens, how this robot will follow, always normal to this more or less spherical part. And the cuts you see they are always different, highly complicated to do by hand. It's almost impossible to map a path like this onto a shape like that. And this gets even more complicated, as you will see later. But we're treating it like it's always the same, which is important to be efficient and to be on time, on price, and to somehow fit this into a market, a market approach, like that you can actually pay for it, or a client can pay for it. So after cutting, you assemble. This is like when it's assembled, you get this giant wall. we moved forward into another level, or Greg chose to, really use toys rather than an appropriate toys. And here the problems get even bigger. Cutting, these are really complicated parts to operate on. So the challenge is simply, how do we manage, how do we create the data, and how do we keep control of that, what the robot is going to do for us. After assembly, it's usually just a process of labor, just skill, simply being able to work with your hands. This gets extremely complicated when the part gets even more complicated. And then you put these pieces together. We then moved into even larger, the most recent, these large fountains, which are then hundreds of parts joined into this large composition. Tolerance becomes a major issue of to bring all parts together all around. Another project that appears to be much simpler, but it's as much of a challenge in programming is these pebbles out of plywood, where the idea is to machine the whole pebble with one motion series, one batch, like you mill around, like you can sort of imagine that. The way we did this is that all we have to really make sure is that the robot can always reach over one hemisphere of plywood. So we had to generate some sort of louver system, control louver system that would give us the normals for the bit to point properly to the part. And then you have a series of these control surfaces. This is like with points turned on. So you have thousands and thousands of points in space that need to be delivered to a robot. We don't really look at these points much. I mean, we're just amazed how much there is actually needed to accomplish something very simple like this. A stacked plywood stock that gets then machined. In this case, you can turn this on, you walk away for 4 hours, and it's done. It's a major difference between a non-digital fabrication and a digital fabrication. That's really what it comes down to, that you can walk away from it while it's actually working. And then we'll finish this. This is then again the labor part, putting the gloss coat on. A similar project which does the same thing again with a different shape, breaks it down into a plywood stock, it machines it. In this case, we did this actually in 3 days. The entire process from receiving the design, cutting the plywood sections and milling the part, and assembling it into this final object. Another furniture project that appears rather simple, but actually I believe this is almost impossible to do without a digital tool, is a honeycomb table base cut in a tulip shape, a torus. Once you have a digital model, it's again, we have to design the motion path of the robot, of the three-dimensional. There is no automatic software. It's because it's so complex to be efficient in relationship to material. We have a major issue with this project of grain. How do you cut in direction to the wood grain, not to destroy the wood, to achieve this very clean, finished product? Another project that you may have seen was very recently, for us, a major deal in a way to take a robot to the site. And this was for Patrick Tighe, his latest exhibition here at SCI-Arc, where we used the robot on site and carved the interior of the space based on a complete digital setup. Like everything was anticipated in a computer, and without any testing, we went directly to the site, stood it up, put it in these positions, which you kind of see on the bottom, and elevated, and executed the motion path of milling these panels. And that was the result. after, this is about 2.5 days of work, carving through these inches and inches of foam. Another project that was done here for SCI-Arc, for Hitoshi Abe, his project, and now a much different scale, greater scale. Here you have a design, a perfect computer model that includes all the components, all the gussets, all the parts, all the cables, everything. For us, what was left was to produce the components, the parts, that then come with assembly, make the whole. And here's some mold making involved because there's some fiberglass work needed for the shell, for the inner shell, that then is digitally cut out. It's a lot easier than to do this with patterns, or almost impossible to do with a pattern. It's a complex surface fiberglass parts. The tubing that was around the hub and the compression ring is pre-rolled material, and digitally we cut that. We dimension these pre-rolled parts with the robot. So we have them set up in front of the machine, chop the ends off of the units, because the outer compression ring is not a circle, or it's made out of it's kind of a free form and made of 14 different parts. And then there's at the same time we produced a jig for positioning all these gussets. So it's literally it's a straight translation from the original computer model into a setup and into an operation that then achieves results in these parts. And there's nothing ever measured. There's no drawing ever made. And again, going back to non-digital fabrication, just an enormous difference. A drawing, a dimension, having a guide, dimension pieces, position pieces based with a measuring tape is unbelievable difference. It's something that doesn't really seem to be such a big difference, but to us, making it and pricing it, it's enormous. And then you achieve the project at the end. And the last project I'm going to talk about it real quickly is the facade project for Tighe also. It's 125 panels, 36 designs. It's a very straightforward project, but benefits from a digital process, of course, enormously. There's no limitation in pattern and design, really. We just have to literally take the 2D design and just follow the cut and just make sure that we know what it takes to mill through aluminum. And then that has implications of how you program, the speed, how many points, the accuracy, how many passes you can mill down, and the nature of the treating aluminum. So to finish this up, we're pretty much tied in. We're kind of this really hands-on situation where design is the sort of desire on the one side, and it shouldn't change. It's majorly important to me that that we don't go back to the architect and say, you got to change this. This is not going to happen. On the other hand, we have material and efficiency in initial programming, because that's what you really pay for with one-offs. If you mass produce, it becomes a non-issue, but if it's small production or single objects, it's a major player, because it's all your labor is in front of the computer rather than out there cutting patterns or something, or plotting a design out and getting going. Thank you.
So first of all, thank you, Marcelo, for figuring out how to put this whole thing together. It's been amazing. This is really exciting for me to see all this interest in composites after 30 years of trying to encourage people to consider these materials in architecture and construction. I think you're a little overly generous, Hernan, in saving. I don't think I really saved your life. I was actually saving my life, and you were just along for the ride. I think actually we could have lasted a little longer out there. First of all, first I'd like to introduce Josh and Nick and Marco and Justin. Where are you guys? Okay, I mean, this is our digital fabrication department, and I think that's also an example of something that's changing, that at least I've seen change. These guys are all smart, well-educated architects who chose to work in a shop environment rather than an office. They could have done either. They've done both in most cases. And I feel fortunate, but also rather excited about the fact that there are a lot of really talented people out there that have that kind of education, but that feel as though they'd like to express themselves building things in a shop. And nobody does anything in our office that can't go out into the shop and do it and make it. And these guys are no exception. So I was reading this thing that Marcelo wrote, and then I read it again and again. And finally I came to the conclusion that I think what it's saying is that I get to say anything I want to say about pretty much anything I want to talk about. So I'm going to start out with my standard kind of slide to remind everybody that composites are not new. They're actually about the oldest man-made material. The Israelites are the first organized manufacturing facility for composites, and they built bricks, and the Pharaoh took straw away from them and punished them. And so without the fiber, they were no longer in production. It turns out, however, that Neolithic man built huts and structures out of composites, again, natural fiber reinforced materials. And I used to think that was sort of the earliest use of composites until we did a job for the American Museum of Natural History, where we were working on replicating and enlarging an oviraptor egg found in the Gobi Desert, which it turned out to have been built in a nest made of mud and straw by the dinosaur. So it's a pretty old concept to use reinforcements and matrices. But it turns out that if you use more and more efficient fibers and more efficient matrices, you get higher and higher performance until finally you get into the kind of things that Professor Meyer was talking about and Kurt Jordan, very, very advanced composite materials, very strong, very light, and very costly. And our role in my little business, ever since we started it about 1980, has been to try to find ways to use this material in the built environment in today's world for purposes that are cost-effective and useful in today. And early on, in addition to movie sets and theater sets and signage, we also stumbled across the fact that composites can actually pretend like there's something that they're not. They actually do a pretty good job of mimicking other materials. And so for a long time, architects knew fiberglass as a cheap alternative to the real thing when they couldn't afford the real thing. That's an example of a building. The bottom 15 feet or so is all FRP, replicating a terracotta building. And that's done. I mean, there's a friend of mine who has a company in New York who takes you on a tour of Manhattan and can point out 14 linear miles of FRP cornice as historic replicas of the original terracotta or sheet metal. But it turns out that something else happened when we were starting to work with these kind of historic buildings, and that is that in the case of this archway, which was completely demolished in the 50s and replaced with sheet metal painted to look like granite, when the tenant moved out and the owners took possession of the property again, they wanted to put it back to the way their great-grandfather had built it in 1906. And so the decision, they looked at different materials. We and a couple other companies were asked to submit a proposal, and we were selected to do this out of FRP for a variety of reasons. But probably the most important reason was that our material was much lighter than even the GFRC alternative that was being considered. And so how often does lightweight really matter in architecture? I mean, you know, we're used to building things out of concrete and stone. I mean, we crawled out of caves and we've basically building, you know, concrete caves around us ever since. So they're heavy, they're massive, and weight doesn't really, I shouldn't say concrete caves around us ever since, but we have been sort of working with gravity as a component of construction that doesn't really lend itself to needing anything that's very light. Our materials are heavy, and so work with them. However, this building, being built in 1906 with a hand-carved lime or sandstone facade, wasn't strong enough to meet the new building codes. So all that structural steel that was behind what was originally limestone or sandstone, and which was strong enough at the time, wasn't strong enough if they put back the original stone veneer. In fact, even if they put back a GFRC system as it was being proposed by our competitor. So the idea that an FRP system allowed the original structure to stay in place was the main reason why this ended up happening in FRP. Costs were about the same. And that led to thinking, gee, these materials have intrinsic properties and value in and of themselves. What would be really nice is to quit trying to pretend we're something different and try to be something that nobody else can be. Try to offer something that can't be done with traditional materials. And along came this project. This is Davey Symphony Hall in San Francisco. And the concert hall was built, 30 years ago, and it was never really sounded very good. The walls, it turned out, were too far away from the orchestra, and the sound didn't bounce out into the audience very efficiently. So they hired an acoustician who explained this to them and said they have to build a whole set of walls that move in closer to the orchestra and aim, and are designed in a way that reflects the sound properly. All these surfaces have to be broken up. There have to be compound curved surfaces. And by the way, the panels have to weigh 40 pounds a square foot. Well, the obvious choice is precast concrete. And we were asked to make the tooling for that because we do a lot of complex mold making. And in the course of the conversation, it began to become clear that precast concrete, although the least expensive way to make something weighs 40 pounds a square foot, was too heavy to pick up in that building. The building was already finished. The roof was these relatively light trusses, and the engineers wouldn't let them rig off those trusses to pick up those panels. That panel that's up right now is one of our panels, and it's rigged from a light electric wire winch to the trusses, but that panel at 40 pounds a square foot would weigh about 9,000 pounds. Way too much for the roof trusses to carry. So what to do? We got to thinking about this, and it occurred to us that the panels didn't have to weigh 40 pounds a square foot when you install them. They only had to weigh 40 pounds a square foot when the orchestra started playing the music. So why not engineer them for a heavier dead load, engineer the connections, the structure, the system for a heavier panel, but build the panels out of a double-walled FRP, a hollow cored FRP. And that would make it possible to make a very lightweight but strong panel, and then lift it up with an electric winch hanging from the trusses relatively easily, bolt it to the system that was supporting it from behind, and then after it was installed, come along and fill the panel, the hollow space between the two FRP skins up with sand to bring it up to the 40 pounds a square foot. So there's 57 tons of sand in the Davies Concert Hall panels, and that was, I think, one of the earlier applications that we had the opportunity to do that utilized FRP for its inherent properties that was just plain not, at least I don't know how else you would have done it. Then along came, we do a lot of large-scale sculpture, and it's an interesting opportunity because the building codes are confused about what to do about sculpture. They're not occupied spaces usually, so you don't really have to worry about a lot of the code restrictions, but you do have to meet wind and seismic requirements, and depending on where you are in the world, that can become rather rigorous. This is a sculpture we did for the artist Klaus Oldenburg and his wife Kosha. This was the first of what became 15 large-scale projects for them. And we got this, again, because FRP was the only way they could figure out how to do it. They had been working with other fabricators for years using metal, and we were asked to digitize. We were doing a lot of laser scanning, still are, but way back then, that was in the mid-'80s, there wasn't very much laser scanning. We bought a laser scanner from a farmhouse in Kentucky, which we later found out was a sales agent for the CIA. And I don't know what they were doing with this laser scanner. I'm not sure I want to know, but at any rate, that was our very first laser scanner. It was a cyberware scanner, and it was primitive by today's standards, but we've been using that for quite a while, and we used that on this sculpture, which was a maquette that we used to capture the shape in the computer, and then the problem they were having is that the structural engineers couldn't get enough steel inside the envelope of the skin that was to be cast aluminum plates in order to make it strong enough to meet the German building codes. This is in Frankfurt. And so what we were able to do is show them that if you just forgot about the steel inside and engineered the skins of the sculpture, you could actually get to where you needed to be without a structure inside. And as long as you design the skins properly, you could satisfy the code officials that this piece was going to work. And so that's where, again, Kurt Jordan, who we've worked with for years, came along, and he helped us develop a finite element model that was convincing enough. And this was built with a CNC router that we built out of wood. It's a plywood and had a little die grinder in it, and it was a two-axis router. And that entire model was built in 1-inch thick slices of foam, kind of what we called stereo or petaluma stereolithography, which is where our shop was at the time. This was the first, I think paperless. The only thing paper on this project was the purchase order. This was for 20th Century Fox. Alex McDowell is the artistic director, I believe, on this project. And this is a movie called Minority Report. And again, this was an all CNC generated or all digitally generated building that we milled out of foam. And in that case, it's just EPS foam on a plywood framework that we fabricated also using the 3D data, all cut on a CNC, and in this case, a 3-axis machine. But there's nothing about that couldn't have been reversed, and those could have been forms, or foam could have been used as forms, and those could have been precast panels. And it was very inexpensive, quick. I think it went together in like 2 days down here in Los Angeles. The future of construction is rapidly becoming 3D, as you all know, although the lawyers haven't quite figured out how to keep up with that complicated problem. We're working on I was talking to Mike a minute ago about a job we're doing at Stanford, which is we're required to participate in the BIM model. We're required to provide information to the BIM model, but the BIM model is not considered a construction document. So although we're allowed to use it, we're not allowed to refer to it as if anything goes wrong. I think somewhere along the line, in the not too distant future, that's going to have to get straightened out because the 3D models are so much more powerful. This is a sculpture we did for the artist Lawrence Argent. It's in Denver, Colorado. It's a 40-foot tall, 36-foot tall blue bear. Again, it has a kind of a hybrid structural system. It has a little bit of steel up at about the bottom 10 feet, and then the rest of the sculpture is an all FRP fabrication. This is basically the shop drawing approach. The bear was, areas of triangles were selected that fit into our gantry machine at the time, and then the CNC machine. This is another homemade machine that we still have and use as a 3-axis machine to machine the female molds out of foam. And again, these female molds, this is one of them. The least expensive mold making material money can buy is this expanded polystyrene foam. It's really cheap. It's recyclable if you keep it clean or try to. And it has a couple of disadvantages, one of which is that if you touch it with resin, it melts. So what we do is we just spray some water-based contact cement and put some tinfoil on it, and that produces a surface that we can mold FRP against without damaging the tool. And again, as long as you're only using a mold one time, this is a pretty inexpensive way to produce a female mold. Although I'm fascinated with this idea of just having a flat fabric and pulling wires and having it sort of deform into a shape. That it's got to be the ultimate. I don't know if we can make a bear out of that, but maybe. I guess it's just a matter of managing the complexity. This slide is here in large part because I want to remind myself how important craftsmanship is in this whole chain. We use a lot of CNC machines. We use a lot of powerful digital tools to create and realize these objects. But at some point, these things have to go out into the shop, and they have to be built, and they have to be put together. These materials have thicknesses. Oftentimes, the models that we get have no thickness. They have shapes that are too big to ship. They have to be broken up into pieces that can be handled and managed. And all of that is part of, in my opinion, part of the design. And just providing, you know, like a infinitely thin shell and expecting that to be translated into a part is, I think, in large part giving up a lot of control that the architect or the designer has or could have if they wanted it. But if they give it up, then it's gone to somebody else, because sooner or later it's going to have to get done. This is just an example of 3 of those, you know, literally hundreds of potato chips of, you know, sort of pixelated potato chips of panels that made up the Blue Bear. And they all had to be assembled into a form, and that wasn't simple. And there was an awful lot of craftsmanship that went into that, in addition to the magic that comes from the 3D modeling. There's the finished piece. And it's called I See What You Mean. It's a blue bear that came out of the Rockies and saw these foreigners coming into their convention center and said, yeah, I see. So it's blue because the rapid prototyping machine that Lawrence used to make the model that he used in his presentation happened to have blue plastic in it. And when it was done, he kind of liked it, so that's why it ended up blue, despite what he may say now. There's all kinds of, you know, Native American legends about a blue bear, and he stumbled across, and so now that's a completely different story. The bear is, it's a very popular piece, but here's a great example of all the rules associated with construction. There was a huge argument between the engineer and the artist about how close that bear could be to the window. The artist, of course, wanted the bear with his face pressed up against the glass. The engineer said, no way, that's going to deflect in a windstorm. We get tornadoes here in Denver. You know, it's got to be at least a foot away, 2 feet away. Well, that's ridiculous. I mean, it's not going to bend 2 feet. Our engineering would show that that's not going to happen. And he said, well, yeah, but the building will move also in a windstorm. And so his criteria was that the wind was going to be blowing from the east on the downwind side of the building and from the west on the upwind side of the building, all at 150 miles an hour. And the clearance between the 2 spaces had to allow for that kind of deflection. So, okay, so it had to be like 8 inches or something. And then along came the guy who's in charge of washing the windows and said, well, there's no way I can wash the windows. I can't get my equipment. And so now the bear is about 1.5 feet away from the wall. So it was the maintenance guy that everybody forgot to ask that really had the answer all along, and it could have saved us months. This is an interesting project. It's been mentioned earlier. I really do think it represents an important step in the evolution of construction. We were fortunate enough to get to do it. Miranda Leonard was a designer. She's a furniture designer who does a lot of work in composite materials. And she wanted to build this house in Tiburon. And she'd been working on it for years. And this represents the plaster model that was an enlargement of an earlier hand-carved small plaster model that she carved basically by hand with the help of, and with a lot of, you know, early 3D digital assistance, going back now maybe 12 years. We finally got the shape the way she wanted it. She was meticulous attention to details, and also very environmentally conscious. For instance, there's no traditional plywood in this building because of the phenolic glue. All of the plywood she built the building with, where there was plywood, like on the floors, was a special plywood with an epoxy glue. The scan data, of course, can be sent off to the architect for construction documents. So this was a truly sort of reverse engineered project where the architects took the 3D scan data and developed the construction documents, figured out all, and which is one of the great things about these 3D models now is architects have the freedom to start playing with these complex forms and still manage the building, manage the HVAC, the electrical, and all of that kind of thing. It's changing the game dramatically. But here's the 3D, this is a model of the piece that we sent to Kurt Jordan, and we inadvertently didn't tell him which end was up, so he picked what seemed to be the obvious, and it was on its side. So the first finite element models are calculations of how this building would work if it were not horizontal. which was our mistake, but didn't, fortunately, with Kurt's so fast at this kind of stuff that it wasn't a big problem. And we got it figured out, and in the end, that building, which consists of 9 pieces, that surface is a thin 1/4 inch of Portland cement stucco. Is my time? Okay. I'm done. That's the last, second to last slide. That's the last slide. That's an all monocoque sculpture garden for Todd Williams and Billy Sin, trying to get it built at their museum in Phoenix. And again, it's an all translucent FRP system. There's no metal in there, and it's naturally convection cooling. So it's I think where we could be, and we could be not too far from now. That's it. Thank you.
Thank you, the 3 of you, for fantastic presentation. What I can do is maybe throw 2 or 3 points in reaction to what you guys present, and then maybe just directly open for questions for the audience, and then we can break up for lunch, because if not, I think we're never going to make it out of here alive. So it seems to me like, well, the three of you that represents 3 different angles where I will say it's a similar table that everybody in this room is trying to establish another conversation. So 3 points that occurred to me to establish in this conversation. One is, first, historically, design, architecture, materials, fabrication, they always have a kind of a symbiotic relationship. But it seems like in recent time, through the power of computers and some other elements, this notion seems to be collapsing almost into one territory. We are not quite there yet, but it seems that we're getting closer and closer that design, assembly, fabrication, design effects, design methodologies, and fabrication are coming closer and closer. And I think it has to do with the tooling and the translation, but also I think it's changing what I would call the ethical or the ethos of how we operate in relation to that. And I think the 3 of you, as I said, represent different ways, because, I mean, for example, Andreas, the way you work is in close collaboration with the designers and so on. Bill, a little bit like that, but also some more established in relation to kind of I will not call it traditional fabrications, but it is embedded with that. When Achim already had to do much more with the design ambition and design sensibility and so on. So the 3 are sort of overlapping, but also establishing different points. So a couple of more, I would say 2 more points that I would like to introduce to this one which is, I would say, the technical geeky part. It seems to me that in one way or another, we still trap into some notion of molding. Like mold is one factor that doesn't seem that we can completely leave behind. This is more specifically more for Bill and Andrea, and I think Karin is trying to work with different logic, which is start to figure it out, the whole design, form finding in relation to that. But I will say for you, the question I have, which is one close to the heart of the discussion, is part of the thing is if what Andrea says and the robot can pretty much do whatever they can do, what really still is the role of form finding in this process when we know at this point that pretty much we can do everything? So again, all these seems to be disconnected points, but ultimately for me have to do with where we move from here, in the sense of, I think all the people present in this conference, I think represents the most progressive side of how we operate in our field, but also a word that I really never liked that much, with the notion of hope, that we can keep hoping that we can get these things done and moving forward. But I will say the main point, the main question I would like to throw there in relation to all these disconnected points and things I'm trying to make is, if the problem of the common language and the notion of how the common language, how far we are that all this will start to collapse into one notion. That in other ways, it's not that it's going to be a kind of a conceptual decision for part of the designer or the architect or the fabricator to start to be in sync, but it will become an instrumental way that you work. That it almost will be impossible to detach. And nobody can anticipate the future, but I think there are many ways how we can get there. And I will open to you guys based on that, and maybe hopefully you can touch in with the specific 3 points that I asked individually to all of you. And after that, I would like to open to the audience for question, or feel free to interrupt and start to raise your hand when we do this, so we can wrap up this by 1:30.
I think when I say it right away, what I think to me the most important aspect is that designers can relax because of the technology that's available.
Help is on the way.
I think you can actually relax, you can focus. I mean, architecture design is so much greater than its fabrication problem. It's looking at social, political, spatial aspects. It's servicing a much greater problem than how it's made. And the making used to be, I think, the making was always a big problem, dilemma, because it is the money. And I think that all these powerful digital tools, digital processing, beginning with the drawing, with the 3D modeling, with the BIM, with the analyses, with the rapid analyses, and then the much faster, cheaper production by translating this directly to a digital driven router or saw blade or welder, I think should make us relax. It's just relaxing.
I'll take that.
I think you're right. I think that we are a piece of the puzzle, but we don't have any aspirations or claim to design, and we just feel like I think that what's happening here is that we might be looking at.
But you are influencing the way that the design is made now. I mean,
sure.
Many architects are incorporating that much earlier in the process.
Well, it's because they're learning the tools. They're playing with them, I think, in a way, and they're sort of discovering or rediscovering a control, a level of participation that architects had before the Industrial Revolution. It's only, when they started cranking out I-beams by the millions of tons, which is like the most inefficient structure. I mean, it's only the right size in the middle, right? But it happens to be the way they make it. So you're stuck with this handful of tools, and architects for 100 and some years have been trapped having to use sort of what was handed to them by the construction industry. That's all changing. The 3D computer models are giving architects the freedom to take control over the design, and I think it's a great opportunity. They just need to recognize that it's a collaborative thing, and I think a different kind of collaboration than had been done in the past, which is more of a, I think in some ways a very unfortunate sort of adversarial relationship with the other members of the team.
I mean, I don't really see that kind of dialectic between saying we can actually collapse all these processes into one, and that actually liberates the designer to whatever he wants to do anyways, because I don't think that, at least when I speak for the kind of research that we are doing, this is about actually solving problems. And this is actually about the kind of generating sort of design possibilities that you would actually not, wouldn't be accessible to you if you wouldn't actually understand the material much better. And funnily enough, actually, Philip Ball in his book Made to Measure quotes, for example, wood as one of the most important inspirations for composite engineers. And I actually came across wood only talking to actually some of the most advanced composite engineers who actually look at, if they really design complex parts, look at the way trees are actually allocating fibers in the kind of twigs and branches and all that stuff. So I think it's, I would say there's a kind of design potential latent in looking at the materials that we already have, and actually from that also maybe spinning off ideas of how we would actually want to design those materials when we can actually do that. That is actually an incredible sort of source of inspiration for doing material sort of based architecture. But it's not, I think it's not that, and I think there's also the great misconception about Froech work is that this was all sort of structurally efficiency driven, which if you really look at it, that's only one part of it. No? That's only sort of that, obviously if you use physical form finding, the material finds a kind of least energy sort of equilibrium, and that turns out to be structurally very efficient. But that wasn't sort of the only reason for the inquiry. For that, he did too many things that actually didn't make sense in that regard.
See, I would argue that tying the fabrication process to your design process, I think, is a limitation you really don't have to do. You may be used to do it, or you kind of think you need to do it because you keep budget and you try to keep a control on budget. And eventually, I think what's been popular is to find inspiration in this fascinating looking process. When Greg does the toy furniture, he didn't think about a robot. I mean, he thought about the major impact, the provocation of using a toy and making a base out of it and putting it into a public space and saying, that's it. I'm
being told for our master of ceremonies, it's not going to be time for questions from the audience. Save it for the end of the day. So to conclude, one thing I would like to touch in relation to what you just say, Andrea, which I completely agree. The last point I wanted to make is it kind of interesting to see already 7 presentations plus 7 what we're going to see in the afternoon to start to see that many of these tools and many of these logics are becoming absolutely almost standard and common. And I think, again, we're going back to the idea that the design ambition or design idea can be not completely liberated, but certainly is part of is embedded with the conceptual logic that you can have. So in that sense, that's what I was saying about the notion of progress and hope, in the idea that many of what the computational power unravel in terms of the design opportunities, they are almost, again, liberated from certain constraints. To one extent, we know there is all the commercial efficiency, budgets, all those things that they will never go away, but they were always part of the problem of design architecture at large. Anyway, I think it's time for break. Any announcement?
Yeah, there's a taco truck, or there's like food around.
Yeah, there for the audience, we have a couple of very LA taco trucks and other sort of food, mobile food outdoors. So go refuel, and we'll resume at 2 o'clock. Okay, thank you.